Now let's come back to what we realized right in the beginning. Biology is driven by chemical reactions. And from our recap into statistical physics, we realized that chemical reactions are characterized by the chemical potential of the system. Now let's look into chemical reactions in general. Let's assume we have two compartments, A and B. A is filled with particles A and B is filled with particles B. Now at the beginning of our experiments, we take away the barrier between the two compartments, and the two particle types can interchange. Further, we assume that there may be a chemical reaction going on. Particle A can get particle B, and particle B can get particle A. Now, the way to describe the equilibrium in the system is that the chemical potential, mu A, must be equal to mu B. Now, mu A is given by the kBt times the log of the concentration of particle A plus some chemical energy epsilon A must be equal to the same for the other particle, where again the concentration of particle B appears. Now, taking this equation, we can solve this equation, and we obtain that kBt times the log of the concentration of particle A minus the log of the concentration of particle B is equal to the change in the zero chemical potential of particles A and B, which for the time being we assume those two particles don't differ too much in, for example, in their mass. Hence, this is equal to the difference in energies, chemical energies of particle B and particle A, epsilon B minus epsilon A. Now, rearranging this last equation, we get an expression for the ratio between the concentrations of particle A and particle B is equal to the exponent of the energy difference between particle B and particle A divided by kBt. Hence, it's the energy difference, chemical energy difference between the two particles that will decide on the relative concentrations in the final situation. Now, keeping this concept in mind, let's look on an example. And the example is the burning of hydrogen, H2. In burning of hydrogen, we start with two hydrogen molecules, 2H2. We add oxygen, one oxygen molecule, O2, leading to two water molecules, H2O. Now, in terms of the chemical potential, what we need to consider here in equilibrium is that the left-hand side, characterized by a chemical potential of 2 times mu H2 plus mu of the oxygen molecule, must be equal to the product side, which is 2 times the chemical potential of a water molecule. Now, using the expression above, hence we can calculate the final concentrations of all the substances, and we obtain that the concentration of the water molecule divided by the product of the concentrations of the hydrogen molecules times the oxygen molecules is equal to e to the power minus 1 divided by kBt times the difference of the chemical potentials of the left and right hand side. So it's 2 times mu 0 of H2, H2O of water, minus 2 times mu zero of the hydrogen molecules minus mu zero of the oxygen molecule. Now the right-hand side is a constant characterizing this particular chemical reaction and is called the equilibrium constant, K equilibrium. You should realize that the equilibrium constant has a unit, and the regular unit, is defined as 1 per molar. Now, for that particular reaction, the difference in the zero chemical potential is 457 kilojoule per mole. Now, it's good to visualize what this difference in chemical reaction energy really means. Let's assume we react 2000 mole of hydrogen with 1000 mole of oxygen. So what we are actually doing here is we react 2 cubic meters of hydrogen with 1 cubic meter of oxygen. What our above expression allows us to do is to calculate how many free hydrogen molecules are over at the end of the reaction. So we just fill in the numbers, and what we obtain is that the number of molecules, the probability that I still find a hydrogen molecule, is 3.4 times 10 to the minus 24. Meaning from the 2000 hydrogen molecules, there are only 2 hydrogen molecules which are not reacted after the reaction had taken place. Now let's further generalize our findings. Well, in a more general case, there are even more reactants and also products. Let's consider a very general chemical reaction where we have nu1 particles of type X1, which we react with nu k particles of type Xk, and the chemical reaction will result in nu k plus 1 molecules of type Xk plus 1 plus all the others ending with nu n particles of type Xn. Now in this situation we just extend our considerations that we did before, and we find that the product of the concentrations of all products divided by the product of all concentrations of the educts is equal to an equilibrium constant, where the equilibrium constant is given by the exponent of minus delta mu 0, so the sum on all the chemical potentials divided by kBt. Now, this very general equation is called the law of mass action. So the relative concentrations of all products and educts is given by just one constant. We have to realize that this constant depends on energies which are involved in the chemical reactions and on temperature. Now, there are still a few more definitions that you will find in literature. So not all the people will talk about the equilibrium constant, but rather its logarithm. And here in particular, the logarithm with the base 10. And then it's called the pK value, and pK is equal to minus log 10 of the equilibrium constant. And there are even more special ones. For example, for the reaction of water into hydrogen and oxygen, This is characterized by the pH value, as defined by pH is equal to minus log 10 of the concentration of the final hydrogen ion, H+. Okay, so finally we're set to turn to the real question we started with. And that relates to the free energy of the ATP turnover, the energy unit in a cell. So in the ATP cycle, we saw that there is an equilibrium between ATP, adenosine triphosphate, with ADP, adenosine diphosphate, plus some inorganic phosphate. Now, at standard chemical conditions, that means all concentrations are set to 1 molar, the delta G, the free energy of that reaction, is minus 13 kBt. So you could now think that this energy is the typical energy that is involved in all those reactions. Yet, we should realize what we did now before. And we have to realize that the chemical energy, the delta G, actually depends on concentrations of all the components. And that will lead to a very different energy that is available for one ATP. And this will be a really surprising result. Okay, so let's look on the law of mass action that we just derived and obtain the free energy from that. And hence, in general, we find that delta G is equal to minus kBt times the log of the ATP concentration minus the log of the ADP concentration minus the log of the concentration of the inorganic phosphate plus delta G0. Let's look in the concentrations that typically you will find in cells. So cells are basically filled with ATP. So the typical concentration of ATP is 1 millimolar. On the other side, the ADP concentration is very low. So it's typically 10 micromolar. Likewise, the phosphate concentration, so there's a lot of inorganic phosphate in cells, is typically, again, high. It's 1 millimolar. By using these concentrations, filling them into the above equation, we obtain that actually the delta G available in a typical situation for a cell is not 13 kBt, but it's 24 kBt. Hence, in the cellular situation, the standard chemical potential in the ATP-ADP equilibrium is different. And that I have drawn here in this very simple graph. Here you see on the y-axis the delta G per kBt as a function of the ADP concentration in the cell. And you see that the delta G will vary with the concentration of the ADP molecules. This is a situation that we actually will come back to in lecture 3, where we discuss molecular motors and how you can in detail understand how molecular motors are working.